Hello, everybody. So last video, we talked about basically how to use a curve, a graph, and the area under a curve to determine probabilities of certain random variables, namely continuous random variables with a normal distribution. And we did a few examples where we found probabilities of a random variable with a standard normal distribution. But of course, there's not just one normal distribution. You get a different normal distribution for every different choice of mean and standard deviation. And we said that the general shape of the curve is the same, but it's always going to be centered at whatever the mean is, and the inflection points are going to be exactly one standard deviation away from the mean. So we're looking at curves like this. And in the past, it would be very kind of difficult to do this. We have to use tables, but now we can do it very easily using our calculators. So just wanted to that's what we're going to do. And so now we'll assume that x is a random variable with a normal probability distribution with mean mu and standard deviation sigma. And so now if we wanted to find the probability that x is less than or equal to a, or just strictly less than a, doesn't make a difference, that amounts to finding the area under this curve. Now the only difference is this is not the standard a standard normal curve. So whereas normally we would use normal CDF with negative infinity a 0, 1, we just replace 0 with whatever the mean is and replace 1 with whatever the standard deviation is. Okay, so now we have, all right, so we would use this with mu is the mean, sigma is the standard deviation. And if we want to find the probability that x is between a and b, then that's the same as this area, and we use normal CDF ab mu sigma. And if we wanted to find the probability that x is bigger than b, we'd want to find this region, and we would use normal CDF of b infinity, because the right endpoint really is infinity, mu and sigma. Now, about these infinities. Okay, so if you don't have infinity on your calculator, if you have a real advanced version of your calculator, you might be able to do that. But if you don't, like I don't, just replace it with a sufficiently large number. Now, the only thing here is you have to make sure it's sufficiently large. Now, when we were using the standard normal distribution, we could just use numbers like 1,000 or 10,000, okay, or negative 1,000, negative 10,000. And that's pretty much okay, as long as you make sure that 1,000 or 10,000 is far enough from the mean. Okay, so basically you want to make sure that whatever number you're replacing with infinity or negative infinity with is at least 4 or 5 standard deviations away from the mean. Okay, so normally that will be okay, but if your mean is 1,000, you obviously don't want to use 1,000 as infinity or negative infinity, right? So keep that in mind. And again, this is just to show you how you could actually do this with the standard normal distribution. If we define another random variable that depends on x, and if we define z to be x minus mu over sigma, we've seen this formula before when we talked about z-scores, but we can actually treat this as another random variable if x is a random variable. And then if we were to see the fact that z being between these two numbers is the same thing as x being between a and b. All right, because up here you could take to subtract mu from both sides from all of these, and then divide by sigma, and you get this inequality that z is between this number and this number. So these areas are equal. So what you could do is you could use normal CDF with the standard normal distribution, just replacing A and B with these numbers. Okay, but of course what we did before calculators became so advanced, they would compute this number by looking it up find this area by looking it up on a table, and then then adjusting accordingly. Okay, but fortunately we don't necessarily have to do it that way. Okay. If you want to use a table, though, you have to do it this way. All right, so just some examples here. In this first example, we have mu is 325 and sigma is 15. So if we want to find the probability that x is less than 330, this would be normal CDF of, okay, so our left endpoint would be negative infinity, so we'll just leave this as negative 10,000. That should be big enough. You could probably take just negative 1,000, will give you the same, but I like to use this. This usually works for negative infinity. Right endpoint is 330, and the mean is 325, and the standard deviation is 15. All right, and again, what this will look like, what we're trying to find is here's 325. That's the mean. 330 would be over here, and we're asking to find what this area is. Okay, and I'm not drawing this to scale, obviously, but that's what the area is, and you don't necessarily have to draw this area whenever you do this. But, okay, so you plug that into your calculator. In fact, I'll just do this right here. So you hit this distribution, choose normal CDF, and like as I said, we will plug in negative 10,000, comma 330, comma 325, comma, and the standard deviation is 15. Close parentheses, enter, and we get 0.631 if we round to 3 decimal places. All right, this would be the probability that x is between 320 and 330. That would be normal CDF of 320, 330, 325, and 15. And if you plug that into your calculator, that turns out to be 0.261. And the probability that x is bigger than 345 is normal CDF of 345, 10,000, positive 10,000. We'll use that for positive infinity, 325, and 15. And on our calculator, that is 0.091. Okay. All right. You will see that if once you get more than 2 standard deviations away from the mean, the endpoints are more than 2 standard deviations away, you're going to see these probabilities are going to get really big or really small. All right, let's say, look at another example. Let's say we're given that the monthly utility bills from a company are normally distributed with a mean of $100 and a standard deviation of $12. Okay, and let's say we select one utility bill at random. What's the probability that bill is less than $70 rather? All right, so in this case, we're going to let X be the cost of the bill. And our mean is 100, and sigma is 12. Okay. So if we want to find the probability that this bill is less than $70, this is the probability that X is less than 70, and that would be normal CDF of negative 10,000, 70, 100, 12. which on your calculator turns out to be 0.006. And this would be an unusual. It would be very unusual if we found that, because we can see that it's more than 2 standard deviations away from the mean. If we want to find the probability that the bill is between 90 and 120, this is the probability that x is between 90 and 120. This would be normal CDF of 90, 20. Those are our endpoints. And then 100 is still the mean, and 12 is still the standard deviation. And this turns out to be 0.750, or 75%. So basically 75% of the bills are between $90 and $120 is what we get from this. The probability that the bill is more than 105, that's the probability that x is greater than 105. And this would be normal CDF of 105, 10,000, or positive infinity, 112. This turns out to be 0.338. And if we want to find a bill that is less than 80 or more than $116, this is the probability that x is less than 80 plus the probability that x is greater than 116. Now, we could do it this way, and we could use the normal CDF command twice and just add these probabilities together. Or you can realize that the complement of this event is the bill being between 80 and 116. So we can actually write this as the probability that x is between 80 and 116. So this will be 1 minus normal CDF of 80, 116, 112. Okay, which is equal to 1 minus 0.861, so this is 0.139, okay, or about 14% of the bills are less than 80 or more than 116. All right, so notice that we did all this. We didn't have to make the standard, we didn't have to convert to a standard distribution. We can, if you wanted to, you can, but I think this is a little easier. And I might do an example maybe on the next video, just to show you how that's done. So that's all for today. I'll see you next time.